coding, where I have been fed and watered and am ready to go. So in the previous session, set up a whole bunch of state handlers, and we got things going to this diagram up the upper left, which is kind of neatly showing us coming out of reset and starting to do some instruction fetch cycles, and there is so much missing from this. But before we get too much detail going, I am starting to build up functions, little static hidden functions in the 8080 that are going to be just, I don't know, a line of code here, a line of code there, but there's going to be a whole lot of them because there are a lot of instructions conceptually in terms of the number of things we put out, and each one of them has a little bit of code in this T state, a little bit of code in that T state, and so on. So I'm going to need to spread this out over multiple source files, and I do not want a whole bunch of functions existing. I don't want every one of these state functions to be declared somewhere publicly. What I want to do is break my parts of the 8080 simulation up into modules and have them interoperate properly. So let's start off with, I'm going to make a reset module. Pragma once, pound include i8080.h. So reset module is going to incorporate all of this stuff, but it's going to work based on the i8080. And we are going to try to not have anything here that knows about reset. So what will be built into i8080.c is going to be a state power on. State power on is going to be very similar to state reset, but it does absolutely nothing. Okay, entirely dumb state. Knows nothing at all about the CPU, knows nothing at all about anything. All of the logic is going to be pushed elsewhere. So let's take a look at what we can do in reset. I want to move reset out to i8080 reset.c. So this is actually part of i8080, so I'm going to be very free about allowing code in this file to muck with the internals of the 8080 structure, because it's the same module. If you really must think of it, think of this as being a new class that is a friend with the old class. But the fact is that all of these submodules of 8080 are very intricately intertwined with the state of the CPU. Their job is to manipulate the state. So state reset is going to be over here. Oh, and these need to be state power on. Oh, wait, did I call it power on? I called it, yeah, power on. We're going to do this for any of these state pointers that we're going to build up in the CPU area. We're going to set them all to power on initially, so that if somebody hasn't hooked up, then we're done. Fetch is going to go in its own file, which is why we don't know about fetch here. So now, state reset goes over in this file. And again, that's going to be the same logic. It's going to say, if the reset signal is low, then we're going to latch the low value into reset int during the phi1 rise, and during phi2 fall, we are going to set this guy to the PC out status, the fetch stuff. Well, this file doesn't get to know anything about fetch. It only knows about what's in the header. So I need a state fetch. And I'm going to need a state reset here. Okay. I may not use these, but I want to have the pointer available. And what we're going to do here is void i8080 underscore reset underscore init of i8080 CPU is going to do everything we need to do to the CPU to initialize the reset subsystem. And this is going to get called from i8080 linked. So everything is all hooked up, and now we're just going to reset we're going to set up the reset. Got all that set up, and we say i8080 reset init CPU. We could actually do that before establishing our edge handlers. That way, if reset init mucks with any signals, just in general, reset your submodules and then establish these guys. And this guy can muck with all the signals he wants during his initialization without triggering any of this. Hopefully he doesn't, because that would require incrementing tau, and we don't want to increment tau during this. But let's keep it clean. So we call 8080 reset init CPU. That means up at the top, I want to include reset.h here. And this guy needs to say extern. Now this should be the only thing that the reset mod, i8080 reset gives us. Everything else should be handled behind the scenes. So what do we need to do here? Well, first of all, CPU arrow state reset is equal to our state function. So we are going to tell the main CPU that we are going to take over that guy. Okay. And then we're going to say, well, let's see. If anybody turns on reset, let's take a look at the diagram again. There's this whole left half on the diagram that I didn't point out before. This is going into reset. So if reset signal goes high here, internal reset's going to go high here, and we need to be in reset. So when this goes high, we need to have address and data floating and so on, and this needs to happen immediately. So I'm going to leave that on the screen where it is. And I need to move it out of the way because clicking on the editor puts it in front. What you do here is set up a handler for the reset signal. So edge on rise of CPU arrow reset i8080 reset. Or should we just call that reset rise? Okay, use step FN here. No, I didn't have a. So if I go down to step, let's make this a step FN so I can do declarations using step FN. Oh boy. Didn't leave my build loop going. There we go. That's better, but not great. Oh, right, because I haven't done any of these. PC out status. This will all go. This is going to go into fetch. Yeah, that's all. Okay, so 2 or more data types. There we go. So what I wanted to do was static step fn reset rise. So if I can declare my step functions like that. Oh, wait a minute. I've been declaring them with the correct inputs. So we're just going to say void. So I don't need to actually change that file. There. So what do I want to do when the reset signal rises? Looking at the diagram here, when this rises, we really want to immediately switch over to using state reset as our CPU arrow state is equal to that, CPU state next is equal to that, and CPU arrow state M1T1. So if we swing into a T1, then it's going to grab state reset as well. And this says that anybody that mucks with next is going to overwrite us if they muck with next after we call this. So yeah, I'm sensing that there might be an issue with this. I'm beginning to sense that we actually need to peak at reset during T1. I don't want to do that. I want to do this on the edge. Well, let's see. Actually, we know something about reset. We do. We know that reset is modified only during this one location here. Okay, so reset, after phi 1 rising, we get a reset. So this looks to me like I need to set my next state during phi 1 rising, not during phi 1 falling. So we'll have to remember that. So as we edit things, we'll set that up. So here we have a problem. We're not exporting phi 1 rise and phi 1 fall, but we perhaps need to. I'm going to make a new header file that's shared between the i8080 sub stuff. Called impl.h, which is known by which all the implementations will know about. And we'll go ahead and include everything we need for an 8080 implementation. No, that's not a good idea, because different submodules don't want to know about each other. They just want to know about this stuff. Okay. That resolves some things. So if the reset internal value is low, We're going to do this in phi1 rise, so it's going to do it before the clock cycle where we sampled it. We're going to say state next to CPU arrow state underscore fetch. And it'll be the responsibility of the fetch module to set state fetch to the appropriate state function to be used when we want to swing into a fetch cycle. Notice that our timing diagram in the upper left is mostly gone away because we have broken the heck out of this thing. But this does mean now that when reset rises, we immediately jump into state reset. Okay. And we should see a phi2 fall in state reset, where we're just going to do nothing. And then starting on the next cycle, on rise, we are going to check the reset on the rising signal of phi1 and gate that into reset internal. And then on phi2 rise, if internal is set, we're going to set state next. Now, we could dispatch entirely with reset internal if we didn't want to plot it by just saying on, here we could just set state next here. But it's cool. I'm going to call this anyway, so it doesn't actually make any difference to our runtime that I know of. We will benchmark this later. We're going to benchmark and performance analyze and trace the heck out of all this code. But there's reset. We see resin goes high and reset goes low. I'm going to put some stubs back in. Stub CPU %s phase equals %t. So we called reset init, and this set state reset, but it didn't set the rest of them. So what I think I'm going to do is I'm going to say if CPU reset arrow value. So this submodule won't know if that's actually required. I'm just going to try it. So if reset is high, we're going to call reset rise to get us into this state. So we'll execute this stuff. And in fact, we could dump this. No, we need to have this up here anyway. So now, bada boom, everybody is unknown. Nobody has set a value on any of this, and I have arranged it so that if you don't know what the value is, I show unknown for it. And we get rid of that new line. And indeed, down below behind my picture, I am seeing that we're in state reset, we're phase 137, 137, 137, and eventually we hit a segmentation fault because guess what? CPU state fetch isn't being set. Okay, so there's our next thing to do. We're going to call this fetch.h. We're going to say extern void i8080 fetch init i8080 CPU. Okay. CPU arrow fetch is equal to state fetch. It's equal to something. And it's going to be these 4 functions that fetch knows about. State X is actually going to have to fork out somewhere else. Now this is a very specific one. This is a state X where it's the last T state of the cycle. And we're saying return to M1. Okay, so this is saying the last T state, not just of this machine cycle, but it's going to be return us to an M1 cycle, not an M2. which means there are some cases in the block diagram. We look at this. Come on. You notice there's x's, like here, double add of RP. We've got an X cycle here, but we've got an M2 cycle coming up. So for RP, this would be an X without the M1. So this is like X2. We'll worry about that as we implement. I'm going to have multiple things that correspond to boxes that have X's in them, and we'll have to differentiate the names as time goes by. But for now, this whole structure here which I've now brought into the proper part of the window so it can be seen on the video, has it. And we are going to say state fetch is this guy. And now we take the declarations for these guys. And we do not put them there. We put them in I8080 fetch.c right there. So it is likely that if we look at that dispatch table on the right there that I've still got up, once we come out of the T3 cycle here, so this op-RD, which is the T3 cycle, state next isn't just going to be state X. It's going to have to be the proper T4 cycle for the instruction, and almost every instruction is going to be different. And the ones that are the same, if we use distinct functions, then we don't need to later on say, you know, do the work, and then if this condition is true, we do the, we don't want to do multiple switches on the opcode decode. So we may have a lot of redundant little tiny functions that do one line and then set next to something very different. This is almost a case where we want coroutines, but there is no coroutining mechanism I've ever seen in the C programming language that is sufficiently low overhead for what I want to do here. So instead, we're just simply storing a function pointer, returning, and the next call goes to the new function, and we're good. So that's got I8080 fetch. Hook it up here. And now, reset init. We also want to do a fetch init. Fetch will be setting a value in the, so it's setting state fetch here. And I believe in reset.c, it's the responsibility of, is it? Yes. So CPU state next is fetch. What we really want to do here is say CPU state fetch M1T1 is equal to fetch. No. Let's take a look at that timing diagram again. I have an extra cycle to work with, and that's going to come in very handy. So here's reset on the right. So internal reset goes low here. Okay? And during this, we're going to be doing the work. So this thing is on phi2 rise here. We're going to say M1T1 is equal to state fetch. We'd really like for this entire period for the ret M1 signal to be set. Yeah, that's what we want to do. So it's this guy right here. So if this is true, yeah, that's the way we want to do it. So if reset is low, we want to set reset int to low. We also want to say edge high of that guy. So now when we get to phase 1 of the next clock, it will automatically set the state from M1 T1. And I can go in and do that. So now this all becomes if phase is equal to phi1 rise, amper 0 is equal to that. Or let's put this as guards. If there. So check phase. We're only doing things during phase 1 rise edge. If reset is still high, then we do nothing else. Otherwise, we set the internal reset low, and we set ret M1 int high, and we specify that next. Let's do that in that order. Specify that the next T state is going to be an M1 cycle. So fetch init. Helps if I don't have syntax errors in my build. So that actually built without warnings. And looky here, suddenly our timing is back. So what are we, let's read the timing thing front to back again. Start out here, we are in power on reset. Reset input floats high sometime during this period, and on phi2 rise, it gets synchronized onto the reset signal. And on phi1 rise, we gate it into the internal reset. The status strobe got released. And then, oh, looky here. We have a M1 cycle starting right here. Status strobe, and we do a fetch. And 4 cycles later, get another sync. So we are now off to the races. We are doing nothing. We're doing nothing with appropriate timing, which means that fetch is hooked up and reset is hooked up. So is there anything else I need to pull out of here? We know about a state power on, which is a no-op, a complete absolute no-op until somebody else sets it differently. We know that we're getting set properly by reset, and we know we're flowing through. Now, we haven't done anything at all with this, and we won't until it is time to start thinking about interrupts. So we're still not out of the weeds. We're still not done. Go back to i8080 fetch, and let's switch our window over to a typical instruction fetch cycle. So we've got a number of things that are happening here that we're not doing. So let's take a look. During T1, we should be driving our address from PC onto the address bus, along with driving our status and sync. But we're not doing that because we don't have one yet. So we need to start setting up registers here. I believe I have a definition for register. And no, I don't. I have a data. So we're going to use data for our registers. And we'll use adder for register pairs. This is an adder PC. So we need a program counter. We now have a program counter. So what else happens here? Well, during reset, when we come out of reset, our CPU's PC is set to 0. Let's take a look at the actual description of what happens during reset. Let me find it. Cycle, state transition. All this is very important information, and we will be going through this sections of this word by word. Eventually, we'll go through everything word by word in this document, but we need to pick and choose what we're looking at. So, initial startup. Systems which require the processor to wait for an explicit startup will store a halt instruction in the first location, so EI halt. Manual, okay. So this doesn't actually say what happens. So I'm pretty sure that the only thing that actually we need to do in the reset stuff is set our PC to 0. It's right there in this diagram here. It's nowhere else. It has to happen before M1 T1. So we're going to say CPU PC is equal to 0. Okay. So that initializes our PC to 0. We still don't have any way of displaying the address and data buses on here. Currently, the mechanism I'm using says associate this row with a given signal and listen to rising and falling edges on it and display its high or low value. And that's going to be a little awkward. It would be nice to have a thing. So we go to fetch.c. So during the rising edge of the PC out status, I want to say CPU adder is equal to CPU PC. Now, actually, it's not going to be that because this is a pointer. It's an array of 1. So we're going to do that. And there. So here we send our address out here. Inc PC, this says star CPU arrow PC is equal to star CPU arrow PC plus 1. Now, the interrupt cycle actually has a signal it uses. You saw me put it in that says don't increment the PC. But we aren't going to be getting into this state function. So we don't need, in that case, so we don't need to actually check that. When we start doing interrupts, I will maybe decide to unify some things to limit the number of functions. But if I do that, that's going to mean extra trips to memory and extra if conditions, which means slowing us down in all of the cases that use that shared function. So we may end up with a lot of functions that differ very, very small ways, which means we need to be absolutely sure that these things are doing the right thing from the beginning, or where we have a maintenance headache, where change one function, we need to change 10 other functions. We may end up with that. Okay, increment the PC. Now here, where we are bringing this in, during Phi2 rise, I want to sample the data bus. Now, on the block diagram, it talks about IR in some of the things. If I look here, we have, yes, instruction register. So during this state op read, we have data coming in on the data bus from a memory. I am going to take it from data and I'm going to put it in IR, and that will drive our logic elsewhere. For now, we're going to ignore it other than print something. So stub adder equals percent. I'm going to do this in octal. Percent 070, percent 040. Oops, those are reversed. We're going to print out what we fetched. Well, IR doesn't exist yet. Carve off the \n. And you can't see it behind my picture, so I will show it there. We are basically saying we have a whole bunch of opcode fetches that are all receiving 0377, which happens to be the value that I left on the bus here. So we only output our status byte for this period of time. So from phi2 rise on the T1 to phi2 rise on the T2, we output our status byte. And then I'm setting it to all bits set to kind of be a visible, I got nothing. Okay, so this means that somebody else is going to respond to the dbn here and give me some data. So I guess our next step is to give it some data. So we have constructed this system that has a CPU, clock generator, control chip, and a decoder. We haven't given it any RAM or ROM yet. I'm going to add a RAM and a ROM to this thing so that we can have it actually fetch from memory now. Let's turn off the PDF because I'm going to need to use more of my screen. So we want pound include of a ROM 8316.h and a RAM 8107x8x4, like that. And test init, we'll want to set that up. Oh, I need to go up here and declare them static ROM 8316. Now, I could actually have multiple ROMs. That's actually not a bad idea. ROM. Let's take a look at our entry points. The ROM is a 2 kilobyte read-only memory. I'm going to have 8 of them. Give me a total of 16 kilobytes of read-only memory, which I'll put in the top 16 kilobytes. And RAM is a 16 kilobyte memory. I'm going to have 2 of those, which I'm going to map into the low 32 kilobytes of memory. So this is actually a fairly deluxe system. Rather than 8, let's have pound define ROM chips 8. RAM boards 2. Okay. Now, there's going to be some trickery getting the decodes hooked up because I don't want to have this code be too comfortable. Well, no, I guess it's going to have to know what the sizes are. Okay. For int chip equals 0, chip less than ROM, chips plus ROM. Oops. We want to do a ROM 8316 init of CPU ROM subchip. Remember, that's an array of arrays. So this ROM subchip still looks like an address. Format is going to be ROM%D. So we have ROM1 through ROM8. And RAM1 and RAM2. And this is 8316 X8, X4. Because there's a lot of individual chips there that we are not actually going to be defining. That's the init stage. Can't do much further until we've finished linking. But once we've finished linking, I can now set this up. So the ROM, I could do a load. If I do a load, I load the value, I load the ROM from memory. And at that point, I'm saying the ROM gets the value, gets the data in a hex file, and as if it started at base. But we're not going to load that. I'm going to leave my ROMs blank at the moment. We're just going to, as part of the test, we will put stuff in it. So we've got ROM init, we've got ROM linked. And RAM linked. Okay, so ROM init, well, it helps if I don't have syntax errors in the calls. Implicit declaration of RAM 8316 X8 X4 underscore init. RAM 8107. Well, yeah. Let's get the part number right. Using an 8316 as a RAM doesn't work very well. Implicit declaration of RAM linked. Well, again, that's the wrong one. It's 8107. And somebody's asserting an edge failed. So, GDB. Where are we? That's inside ROM linked. This is called edge invar ROM ready in. So that guy right there, which means I didn't set the ready input for the ROM. But the ROMs owned their inputs.
Well, Comcast claims that
Just a minute, EdgeNet ready in. Oh. Let's see here. Oh, wait a minute. RDYN is the way that the ROM signals back that it's not ready yet. Right there. Which means that when I initialize the ROMs, do those after all of this before any linked. We could do the thing there, but we need to
I know.
look it up.
They sent you the code that I needed to enter on the computer to check you in. We're not gonna, no, we're just not gonna worry about it. We'll do it when we get there tomorrow.
I'm not sure if the RAM needs that as well. Is there anything else here that I might need? Well, the ROMs have a read signal, which is going to have to be mapped into the decoder. RAM doesn't have a ready in.
What difference does it
So the RAMs aren't going to be doing wait states.
Why does it matter?
Okay, so ROM adder isn't set. Okay, so that should set those up. And this is not ROM boards, this is RAM boards. Okay. So now we want to do the decoder. So I did set up a function to do this, so we just end up writing directly into these arrays. So for the highest numbered chip, which is ROM chips -1, this would be mem pages -2. So I would need to do page +1 and page +2. Or +2 and +1. The other way to do this would be to initialize from the top down. Okay, so that hooks up chip enables for the ROM and the RAMs. Well beyond what I need for this test so far, but get them hooked up so they're there when we need them. The other thing I'm going to do is deck.shadow is equal to the first ROM board. So all of the initial accesses to memory are going to be redirected to ROM 0. And later on, when we null out ROM 0, we'll get everybody in the correct places. We'll be good. So we're still getting this 3777. So we are getting MEMR. So MEMR falls. We are getting a decode.
Hello? I'm doing fine, thank you. And you? Yeah. Yeah. Yeah.
I'm going to use the same debug symbol.
I went to the walk-in yesterday. They start swelling up immediately. We decided, they took x-rays and wrapped it good with this, wrap that they wet and put face bandages all over from stem to stern.
So we're getting here, and this is activating RAM1 read. We are setting shadow to 0 at the decoder invar. That is the wrong place to clear shadow. That needs to be in a init. That was misplaced. Oh, it's done in a init.
Hanging on the wall for a while.
Okay, there we have it. So now we are activating ROM1 read. And here in ROM1 read, we get a wait cycle. Then in fetch, we are getting we're not honoring the wait cycle. So let's put our wait logic in. So the rules for the fetch wait are pretty simple. Let's bring up the PDF and look at them. So wait is checked here. Actually, ready is checked here. So on the descending edge of phi 2, We need to make a decision based on ready as to whether to go to wait or not. So this implements the change that we made in the logic earlier, where if we're in a wait state, we're going to reissue the rising edge without falling edges in between. This may actually draw an artifact for us on the diagram, which will show it, yes, we're reissuing this. And again, we're checking ready. So here in T2, if ready is set, we're going on to op read. Otherwise, we're going to go to wait. And in wait, we're going to check it. And if it's ready, we're going on to op read. And this is not right. That's right, because when we issue that, when this reissues the ROM read, it needs to assure that it puts an edge out. That may or may not have gone into the code. So when we're activating, making edge, this edge go low, we need to make sure it goes high first. And now I can remove this debug because I know it's happening. Well, let's get it working first. There we go. So we get activating ROM rate, activating ROM data, fetch. So this pattern repeats over and over again. Let's make sure this is redrawn. Okay, we need to add more to our plot here. So along with this stuff, sync status strobe, dbn memr, so now we're seeing ready and go low, and we're not seeing a wait come back. So let's take a look at how to build the wait signal. Wait should go high at the beginning of the T1 cycle with wait, and it should go low at the beginning of the T1 cycle, which is not. So let's do that. And there we have it. There is our wait signal going active. We have little spikies on memr and dvn, assuring that, telling us, yeah, we are reasserting that and we're providing an edge for the downstream stuff. So for the simulation purposes, I know that we're getting an edge there. The actual signals as drawn for the CPU will have a just horizontal line across there. That's fine. It doesn't go all the way down, so we know we're not actually outputting a 0 at any point. We may have wait states on other things as well. So these other places where we do edge low, I'm going to force it high first. I am not sure if we have wait states during write. I'm going to have to check that. I think we do. Anyway, I will force the edge here in decoder just in case.
Well, because I've got to continue using the law, but I don't like it because I can't have anything in hand who's contriving me a device to go on the front of it to put something in.
I just ordered you a basket.
Okay, so now this is the data we're getting back from the ROM. Let's set some data up for it. Okay, so with that little bit of jiggery pokery, now we've got fetching. We're fetching a NOP and a 363, a 373, and a 166. And I hope I did the conversion from binary to octal properly in my head. So halt is, let's see, NOP is 0, DI is 3, 110 is 6, 011 is 3, so 363, and 373 for EI, and the halt is a 166. Now the halt is actually a special case of a move instruction. So kind of an interesting way that they packed the instruction set. Move is a 1 in the uppermost digit, and the destination register and the source register. And a destination or source of 6 is memory. Well, you don't move directly to and from memory on the x86, on the 8080. x86, yeah. So the encodings for, well, we've got move RM and move MR. We do have those. Okay, so you can load and store internal registers from where HL points, but you can't move from memory to memory. Okay, that would be a no-op because you'd be reading from a memory cell and writing back to the memory cell. So instead, they took that particular source code, that particular opcode, and that became the halt code. So you could actually define halt as a function. You could define it as a macro that feeds M and M to the move codes. We may do that in the future, but for now, we just got this. So here we are. I'm going to break this up into 2 plots. So the first plot is going to cover through the end of the no-op. So we're going to stop it sometime around here. So I want to print where the sinks are so we can figure out what's going on. Or I could count. So 1, 2, 3, 4, 5, 6, 7, 8, 9. What if I run 9 cycles? Okay, that's got that nice and short. As I said, to go longer, and it didn't have data, so it went shorter. But we still got the right amount of stuff. So there's our nice picture of reset.
You gonna watch the news?
Yeah, I'm playing the game.
Reset into a NOP. Okay, so it'd be kind of nice if the fetch actually printed out its tau value as well. So we fetch the NOP here at tau big number, and we fetched the 377 at that other big number. Okay, and there's nothing really visible happening here. We don't have we don't have an implementation of halt, or we don't have our enable disable interrupts and so on. But at this point, we are running steady state.
Transfer shower home.
And I'm on kind of a roll, so let's implement enough of EI and DI that they actually wiggle the interrupt lines. Okay. Oh, how are we going to do the decode? So what I want to do now is have P8080 state M1T4 of 256. So for each instruction, when I fetch it from M1T3, I am going to go into M1T4 with the opcode and go directly to the right function, which means that if we have one function handling multiple opcodes, we're going to go there. You can do this with small CPUs being simulated by large ones. But let's get this set up. So same trick as before. Before anybody claims a service, claims to want to service us, we'll just toss that into state power on. Now in fetch, where we fetch a init, we say, oh, if we've initialized fetch, then I want the default M1T4 to be state X. As we add instructions, whoever's adding that instruction will write its value in there. And now, where we diverted to state X, we now do the decode. We have now implemented instruction decode in the most general way possible, trading all the space we need for all the time possible. And I am going to reduce the size of this again. So instead of 30, there. boy, the formatter really wants me to have wider stuff here. I tuned it to provide slightly longer lines, and apparently when I changed fonts to use the Sun font, I'm not actually sure I'm still using the Sun font. This changed. Okay, so we're going to go back to using the other font really quick. So back to knit.el. I really like the Sun stuff, but okay. We'll be back in the editor in a moment. I need to turn this off while I do this little scummy trick. Dum-ba-dum. So I want to make this consistent from run to run, so we're going to do all the right things. And turn it back on and adjust the size of the actual editor so that we are the right size again. I believe that's as big as I can make it. That's good. We go back to here. Yeah. Okay. And that looks good. And notice that we are no longer overflowing the window when we do this. So it's not the Sun font, but it's still a good coding font. So EI and DI and so on. We can turn off the PDF. So I8080 underscore enter dot H and dot C. Actually, these guys just, they do need to have the CPU pointer. So this is I-8080 init, enter. So I come into enter.c over here. What do I want to set up inside the CPU structure? Well, I need to set up the t-states so that we have our M1T4. So these are going to be state called EI and DI. These are all single cycle. Yeah, look who wants to talk.
What's her problem?
Huh?
What's her problem?
She just wanted to talk. Okay, so Lucy wanted to check the code out real quick. So what we're going to do is now when we get the op read and we do the decode, it's going to go through this M1T4 array. And for this opcode, it's going to end up in these two functions. You squirming? We're going to print that we're there. The other thing we need to do is actually enable and disable interrupts. Let's take a look at what is going on. I can't really type with the cat on my lap. So for the interrupt timing, int enable is either high or low. It will be dropped low during the process of taking interrupt, which we're not going to start on quite yet. But this means int e needs to be put high when we're enabling it and low when we're disabling it. And that needs to happen on the rising edge of phi 2. Isn't that right, Lucy? You don't need to sit up. She'll be back in a few minutes, I can already tell. But I really wanted to get some more instructions done here before shutting down for the day. So during Phi2 rise here, this is enable interrupt. We're going to say edge, high, CPU, arrow, INT E. And here it is low. The other thing is when you do a enable interrupt, we want to make sure when we write the logic that we get one, if we got an EI followed by an instruction, we can't get an interrupt before that instruction is completed. And the pipelining should work on that. As I said, I've prototyped a lot of this before, and I remember that the pipeline fell into place. So we have here some problems. Op EI is not declared. Well, that's because I didn't include my 8080 impl.h. So what we saw here was we get the fetch from 0, we fetch the 0363, which disable interrupts, and we did indeed get into phase 137, and then we did the enable interrupts, and we don't have a halt. Let's put halt as part of interrupt. Now, halt puts us in a special state where things get weird. Oh, halt timing. Just realized that was in the wrong window. There we go. So here's enable interrupt, disable interrupt, and halt. If we go over here, we see we're not getting there. There we are. So 166 puts us in halt. For now, we're just spinning inside that 1T state, never going anywhere. If we go over to our PDF again, halt timing. So here's the M1 for halt timing. So we've done the normal things. And at T3, we do the decode, we get into T4, and this says that we go into an M2 cycle for halt. And the M2 cycle does have it. We do get a sync, but it's a type 9 cycle. So we're going to do a different M1 T1. Let's really an M2 T2. Okay, so this is state HLT is for the instruction. I'm going to say M2. State HLT. The next cycle is a M2 T1 here. So we have T1, T2, and a WH. Hook those up. So what happens during those cycles? So M2T1, we're going to raise sync. CPU arrow data. So we need to set this to status something or other. And the status is status number 9, which is here, halt ACK. Other than that, it's very similar to PC out status. Let's take a look at this. So we're going to set the PC out. We're going to halt ACK and engage sync, and then set our next state. Well, this guy's still setting it in there. We were going to move those up, weren't we? No, that one needs to be down there. Okay. Okay, during the T2 state, sync goes low, kind of like the PC Inc. Okay. We are not incrementing the PC. We're going to scramble the data bus. And during WH, during the rise, we're going to raise the wait signal. And WHs continue forever until something else happens. And that something else is going to be actually taking an interrupt. So what have we got so far? NOP, disable interrupts, enable interrupts, halt instruction, and we go no further. So what do we want to add to the display on that? I think what I want to do is have a different plot for the halt sequence. So this T0 is this value. And what I want to do is run through the end of the NOP. So the instruction fetch here, When am I printing this? This is in the op read. I need to work out what the offset is to the sink. Oh, God. Thump, thump. I believe that tau, or we're printing the fetch of something, I believe that's at the descending edge of sync. In op read, no, that's here. There's phi 2 rising after the wait state, so that's sometime in here. So back by 9 gives phi 2 rising here, back by 9 gives phi 2 rising here, back by 9 gives phi 2 rising for here, and phi 2 rise, let's do 4 by that. 30-ish? Let's try something. I'm going to count forward instead. So this guy, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, he's good. Oh, 9 times 9. Let's do 10. $11. Trying to get it. Oh, right. I need to extend this as well. 90. $99. Okay. So this is 99 clocks wide. We're getting into the next mem R. We can back it up by 9 clocks to here. Another 9 there's by 18 clocks. This 81 should back it up to just here. Now I could do all this in a single run. I just have to stash taus. So I'm not actually imposing any inputs. So if I don't reset T0, then this guy, I want to start at I want to run the NOP, the DI, and the EI. So T0 is the base here. 1, 2, 3, 4, 5. Puts us here. So we want to go 4 by 9. And the length that we want to trace is NOP, DI, EI. Each one of those is 4 T-states. So that's 12. And in here, so we should be seeing an int E on this plot. There it is. Now int E is not being wiggled. So we're going to say plus 9 times 1. We're going to go really super wide. I just want to see if that line is wiggling anywhere. Okay, so there, we are seeing interrupt enable go high. What am I removing? Oh, RAM-F. I forgot to do that. Doc image I8080 star PNG. Beginning to get frustrated. Actually, that's correct. This is a NOP instruction. And here's a DI instruction which forces NT low, and EI that forces it high. So let's change the order of that a little bit so that I can actually see it wiggle a little bit more. We're going to do enable, disable, enable. How about enable, NOP, disable, enable, halt. Okay, the instruction set it. New instruction list is up. So, enable interrupts, execute a NOP, disable interrupts, enable interrupts, execute a halt. Now I'm going to do another plot. So T0 plus 9 times it was 4. So 4 more is 8, 12, 16. And I'm only going to show a few cycles. I need to give it a different name. That becomes halt. This is EI, DI, EI. These are supposed to be removed. BIST reset, EI, DI, BIST halt. Oh, right, the text files still exist elsewhere. We need to go wipe those too. Log, timing, all those go away. There we go. There's our reset behavior. Reset followed by a probably a NOP. Actually, I think that might even be an EI. Here's our enable interrupt, NOP, disable interrupt, enable interrupt. And here's our halt. I think that's not quite right. Yeah, we need to offset that by 3 more. And 4 more. There we have it. Okay, so notice that wait has more than one use. So here wait is being set because we're in a wait state, which is occurring during the fetch of the halt. This is where I wish I was actually showing the contents of the data bus. And then we go into the instruction after the halt here. And you notice that here we got a memr. And here we're not getting a memr. We're not getting a dbin. Okay, so we are in halt state and wait has gone high. So this gets us into halt. And I think I'm going to call that a day for these sessions. We have a selection of 8080 instructions. They can't really do a whole lot, but they can wiggle signals like mad, which is what we're trying to do here. And I'm going to comment this up and push it on up to the repository. I will see you in the next installment where I will think about whether I want to swing right into doing interrupts, which is big and hairy, or if I want to start by actually writing some real code. I would like to get some actual instructions going on so we can see some internal state changes in the CPU. I will continue to think about how I can display the contents of the address and data buses on this. One of the problems there is we don't actually have a thing that we can say, this is the data bus. When people change the data bus, I have a subscriber looking for changes on the data bus. What we're going to have to do is have something explicit. I don't know. I'll look at the timing diagrams and see if there's a place where I can snapshot the data bus and do something for the trace if it changed. I don't know. Maybe it did every ninth cycle. We'll figure it out. Anyway, I will see you then. But until then, keep it small, keep it safe, and keep